We're going to prove this theorem, and we need this theorem in order to do the max-min test, the first derivative max-min test. So this says let f of x be a function that is differentiable on open interval ab. If the derivative f prime is greater than 0, then the function f of x is increasing. If f prime is less than 0, then the function is decreasing. And if f prime equals 0, then the function is constant. Okay, so first of all, let's see what increasing means. So increasing means that x1 less than x2 means that f of x1 less than f of x2. All right, so that, okay, the second value is bigger than the first value. That means the function's increasing. Decreasing, it would be, again, if x1 is less than x2, then we have the opposite situation. F of x1 is bigger than f of x2, so the second value is smaller than the first value. And of course, constant means that if x1 less than x2, then constant meaning doesn't change, f of x1 equal to f of x2. All right. So now let's go on to the proof of this theorem. And basically this theorem justifies the first derivative test, which takes the derivative, see if it's positive or negative, to determine if a function's increasing or decreasing. Now this theorem uses the mean value theorem. Let's first assume that f prime is greater than 0. Okay, let's assume this. All right, so we'll assume that we're in this case now, that f prime is greater than 0. Let's suppose we have 2 points, x1 less than x2. Then we'll have to show that f of x1 is less than f of x2. Now here's where the mean value theorem comes in. We know we have some point c, and c is in between x1 and x2, such that f prime of c is equal to f of x2, the slope of the secant line, minus f of x1, x2 minus x1. Okay, and since the derivative is greater than 0, this value is positive, or this value is greater than 0. Now we said x1 is less than x2, so that means this is positive. Since this whole quotient is positive, remember f prime is greater than 0, since this quotient is positive, that means that if the denominator is positive and the fraction is positive, this one also must be positive. If that's positive, then this value is bigger. So we conclude that f of x2 is greater than f of x1, or just write it the opposite way, f of x1 less than f of x2. The function's increasing, and that's what we wanted to show. So that proves the theorem when f prime is greater than 0. If f prime is less than 0, then it's very similar. Basically, this will be positive and the top will be negative, and if the top is negative, that means that this value is smaller than this value, or f of x1 is greater than f of x2, which is this conclusion. So it's very similar. The proof is very similar, so we'll just do this piece. Okay, this piece of the proof. And for this piece, it's also very similar type of proof, and so we're just going to leave it at this.